In this video, we present a few problems to help you go back and make sure that some of the key concepts were properly understood. The video is only going to present hints to the answers, and there is a detailed description of each problem at the end of this video. The first question addresses effective stress. Please go back in each of the cases to previous recorded videos. But this one is the case where there is an aquitard. That means that water cannot migrate through. This is like in the extreme case, imagine that we have a plastic membrane, but in reality it's the sedimentary layers that have placed there probably a thin layer of clay. And there is a unique situation that there is high pressure from underneath. This is an artesian case, which can be quite dangerous because if you begin to excavate, you may have a bottom blow up. So we need to understand the situation with pore pressure and effective stress. And so the first thing that we ought to recognize is that because this is a hydrostatic system, wherever I place a piezometer here, it will rise to the same elevation. Therefore, if this is the height of the piezometric head, then I can immediately tell which is the pore fluid pressure at every point, which is the piezometric height times gamma water. So once again, the lower part is under hydrostatic conditions. So wherever you place a piezometer, it will rise to the same elevation. So then the question is, what is the height inside the piezometer, which will be some relationship with the elevation with respect to your first piezometer or a datum that you have established. The second part is that if you place a piezometer from the top, the water is also hydrostatic and it will rise to where the water table is. Therefore, you know the pore pressure everywhere in the formation at the top because it will be the piezometric height at that point times the unit weight of water. Notice that the piezometer immediately below the aquitard will rise to this elevation here at the top. Immediately above the aquitard will rise to the pool table, and therefore the aquitard is indeed subjected to a significant pressure difference, which will tend to drive fluids through the aquitard. This is the case as well for seal layers, for petroleum, for oil and gas, for CO2 geological storage. So with this situation in mind, the only thing that you have to recognize now that you know the pore pressure everywhere is you need to know the total stress in the z direction at every point. And the total stress is computed by adding the weight in this level ground condition is by adding the weight of everything above the point. So it will be the weight of the water, the weight of the saturated sediment, the weight of the aquitard, and the weight of the lower sediment all the way up to the point. So the weight of everything above the point per unit area gives you the total head at depth z. Piezometric height at depth z gives you the pore pressure at depth z. And so now the effective stress in the z direction is equal to the total stress minus the pore pressure. And now you can actually plot the distribution of pore pressure, total stress, and effective stress in the vertical direction everywhere. Furthermore, if you know that the formation is under K0 zero lateral strain condition, it has not been preloaded or yes, you will know also the stress ratio at rest, which we're going to call K0, sigma horizontal effective over sigma z effective at epsilon h equal to 0, zero lateral strain. If you know K0, then for this level ground condition, you will be able to estimate the horizontal stress as K0 sigma z effective. The second question is a review question related to the threshold strain. And I invite you to look at data coming from Boussinesq and Dobry, Shihara, and many other Japanese co-workers and researchers worldwide, and to see what controls the elastic threshold strain. The volumetric threshold strain tends to be 1.5 log cycles larger, so if that means about 30 times larger than the elastic threshold strain. So choose one or the other, but I would suggest that we start with one, let's say the elastic threshold strain, and see if you can identify parameters that eventually govern its behavior. When we did it in previous videos, we showed that the elastic threshold strain from a Hertzian point of view was related to the applied vertical normal force, which relates to the effective stress, and the amount of shear that was required to lose a contact was the point when we decided that it was the elastic threshold strain. And we identified that the shear strain required to lose that contact was directly proportional to the normal stress, because that told you how flat the contacts were to begin with, and also inversely proportional to the stiffness of the mineral that makes the particles. In reality, there is some coefficient and some exponent here that came from Hertzian relationship, but that was a very important concept, that the higher the confinement, the flatter the contacts. It's like when you stand and you bend your knees, it takes longer lateral deformation to detach the far away leg from the ground. This is exactly what this is telling us. And conversely, when it is very stiff, then it takes very little deformation to detach one foot from the ground. So please review this micro-mechanical analysis, which we, by miracle, somehow we make it applicable to the macro scale equivalent continuum, but do it in the context of real data, because it will be indeed most insightful. Similarly, for theory of elasticity, we reviewed the concept of Poisson's ratio, and there is a video on that, and the importance that there is a limiting value for Poisson's ratio for theory of elasticity to remain consistent, for the bulk stiffness to remain a positive value compared to the Young's modulus. So that was 0.5, but 0.5 is also the Poisson's ratio where there is zero volumetric strain, and it comes back from the definition of volumetric strain for a small strain deformation. So please check these values, identify values from the literature, recognize how they were measured, what was the strain level where they determined them. Take a look and be very cautious about it. But the other question related to theory of elasticity was to demonstrate the shear modulus as a function of Young's modulus and Poisson's ratio, which we did previously. Please do it step by yourselves, because it will also give you insight and force you to refresh the concept of stress and strain tensors, which we're going to do it in the form of more circles for stress and more circles for strains, and to understand the important difference between the mechanics shear strain and the engineering shear strain. Finally, I ask you to review the concept of superposition. And the concept of superposition is so important because if we have an excitation X and an outcome Y, and we have a linear system, for an input X1, I get an output Y1. For an input X2, I get an output Y2. And for an input which is X1 plus X2, so we are going to add this one here. This is X1 plus X2. X1 plus X2. Notice that I get an output here, which is Y for an input 1, 2. Let's say that this is x1, 2. But as it turns out, you can move y1 on top of y2, and indeed, you see that this is y1 plus y2. And so the concept of superposition is amazing, because it means that sum of the causes, I add two causes, and I get the sum of the effects. And now, from superposition principle, I can do many things. For example, if I have the load at the point, and I have an induced stress everywhere underneath the surface, now I can put another load along a line, and another one, and another one. And for each of them, I begin to see the impact that they have on that element, and I can add the contributions. So I go from a point load on a half space, which is the Boussinesq solution, to a line load by integration along the line. That is the superposition principle. Similarly, for example, this is the subsurface now. I have a solution for a point load in the middle of a half space. That's called the Mindlin solution. And now I can integrate it, and I can say what happens if I put a little load at that depth, a little load at that depth, etc. And now I have the solution for the deformation of a pile experiences with depth by superposition of Mindlin solutions. Sum of the cause, sum of the effects means the superposition or integration. And we use this in a wide range of mathematical solutions. In fact, the Fourier transform implies linearity. So it's not only for the classical mechanics, it's for signal processing and for solving problems with the Fourier transform as well. So really great potentials and values. Please convince me that you fully understand it. Convince yourself. Finally, was the problem of self-compaction. We identified that there are the compressibility of a soil, void ratio versus effective stress, really looks like an exponentially decaying function, always. What happens is that we plot this one in semi-log scale. So by the time we plot in logarithmic scale of sigma, then we stretch the origin and we contract the long tail, and this deforms like that. But don't be misled. This is really an exponentially decaying function, and there are asymptotic values. This is the void ratio at zero effective stress, and this would be the void ratio as the effective stress goes to infinite. And so I can write equations of the following form. E at any effective stress is equal to E0 minus, and now I'm going to distribute the difference between E at 0 minus E at infinite. In other words, I'm going to distribute this gap here according to some function of stress. And we gave you several functions for that. The hyperbolic, and comes a power model, an exponential model that some of them come, for example, from gas law. Now I can compute how does the effective stress and the void ratio change with depth, because at zero depth the effective stress is zero and the void ratio will be E0, the packing of the soil at zero effective stress. But as you go down, the soil above will apply its weight on the soil below, and so you need to begin accumulating the weight of the different layers above it. But as the weight increases, the effective stress increases, the void ratio decreases, the unit weight increases. And so you can do in a simple spreadsheet, you start with depth, starting at depth 0. The effective stress is 0 in the z direction, and the void ratio is the void ratio that in your material is the asymptotic void ratio at zero effective stress. And with this asymptotic void ratio at zero effective stress, you can compute the unit weight of the material for that very first layer. And the unit weight will be a function of the gamma mineral and the void ratio. Go back and see the equation from gravimetric volumetric relationships. So you will have a unit weight at zero depth. Now we increase with the delta z. I go to the next depth. Let's say I go to 1 meter. And now at 1 meter, the effective stress will be the effective stress above plus delta z gamma of the element above. So I use this gamma now to compute, and the effective stress above to compute the next value of the effective stress here. And with that effective stress, I go back into this formula, and I know what is the next void ratio at that depth. And with that void ratio, I know the unit weight at that depth, and I go back to the next depth by adding the additional contributions. And when you do that, you are going to end up with a profile of void ratio versus depth and effective stress versus depth. Now, furthermore, you have to convince yourself that you didn't make a mistake, so you could also plot the void ratio that you have calculated versus the effective stress that you have calculated, and by doing so, you are going to regenerate the void ratio versus effective stress for the soil. Let me erase and come back with a few other problems. The next three problems are problems of mechanics at the verge of failure. And we have to recognize that to compute the formations, we use the changes in stress that will cause the formation. The initial stresses in the subsurface have already caused the deformation and the self-compaction that they could have. So it is the additional load that the foundation will create or an excavation will create is a stress change that will cause deformations. However, the initial stresses and the stress change, the combined stresses, are the ones that are going to bring the element to failure. So we cannot disregard the initial stresses when we are exploring failure conditions. And so this is the case with a pile. We are going to we have an element here. We have a certain state of stress before the pile installation. And by some magic, we are able to install this pile without causing any stress change. It's a clearly idealized situation, but let's start as a way to begin the understanding of the problem. And so the system has a certain sigma z and sigma horizontal effective, and we are going to load the pile, which is going to cause shear on that element. The question is, how much shear can the element resist, because that will contribute to the shaft resistance of the pile. And so let's draw the initial state of stress before we place the pile. And the initial state of stress in a tau sigma space is equal to the sigma horizontal and the sigma vertical. This is sigma vertically typically being larger than the sigma horizontal effective. This is the failure line. And as you can tell, the element already has quite a lot of shear. So by the time we add shear, so let's say that on the face on the here that it plots horizontally, let's say that we take that one as our face, we're going to plot shear downwards because it creates counterclockwise rotation. We're going to say that it's positive. So shear will appear here, and at the same time, because of reciprocity of shear stresses, shear will also appear on the other planes. And so this will be the state of shear. This element will actually go down. And so there is a new circle that will grow concentrically and that eventually becomes tangent to the failure line. In other words, the element cannot take any more shear. Please notice that the element is touching the failure line at this point. However, the amount of shear that we were able to place is this amount. So if I draw a radial line, this is normal, and that amount, that shear, which would be probably this maximum shear here, it is the maximum shear in the circle, is not the amount of shear that you can add. The amount of shear that you can add is this piece here on the side. So this is what can be tau add. That is the amount that can be added, even though the tau at failure is this amount, but the system already has an initial shear. And so I invite you to play with trigonometric relationships and the geometry of the problem to derive an equation for how much tau can be added, and that will be a function of the anisotropy of the initial state of stress. So it will be a function of sigma z effective over sigma horizontal effective to begin with. Under certain conditions, this value will be quite similar to a value that we tend to use. For example, we tend to say, so this is, once again, let me highlight that this is the problem that I would like to address. What we typically do is, well, the tau is equal to sigma normal, which is the horizontal, times tangent phi. And the question I'm asking is whether this is true. The next problem is a problem of low deformation and volumetric changes that this element will experience if I do an excavation and then allow it to relax laterally. So this is a lateral unloading, there will be lateral extension from a point of view of the geometry of the element. It will get shorter and fatter. And so if we start with this element before the excavation, the state of stress was also under a K0 condition. So this is sigma z effective, this is sigma horizontal effective. So this element is also, if we plot it in a tau sigma space, it is somewhere in this state of stress under typical K0 less than 1 condition. Now, the vertical overburden remains, so the vertical stress will not change much. It will, but not much. And however, the horizontal will start relaxing. So this circle is going to grow towards the left until it eventually touches the failure envelope. So this is the unloading they will experience. And at that point, the soil says, I cannot take any further stress anisotropy, and some retaining wall will have to pick up the rest of the load, that limiting horizontal stress. So if I only plot the apex of the circle follows a 45-degree line towards the upper corner here, towards the left and up. So remember that we can convert this into the apex value becomes Q, and this one we can convert it into the center value, which becomes P, and P prime in this case. And now we can plot all this in a QPE epsilon space. This is QPE epsilon space. And so this case is, once again, lateral extension. Now this is the alpha line. This is not the phi line. This is friction, but we have converted tangent alpha equals sine phi. This is the alpha line. And so we start with some stress anisotropy because there was an initial Mohr circle, and we're going to evolve at 45-degree angles, but let's complete the plot. This is the critical state line. In other words, the locus of points in the void ratio mean stress P prime, where either dilative or contractive materials will evolve to reach to that line, to shear at constant volume. And we could have started with either a dilative or a contractive material. This is the dilative regime, this is the contractive regime. But we know that if it is drained, in the case of drain situations, we know what the stress path will be. It will go at 45 degrees towards the failure line, and that is where it reaches failure. So this element will encounter failure, dilative or contractive will come here. The contractive will evolve in that direction. The dilative, it may itself experience some contraction and then it dilates. So if we bring all these to the volumetric changes, which is void ratio and deviatoric deformations, strain, shear, strain, so this will plot something as follows. They will all end on this line, both end on this line. This one will do it contractively, this one may dilate a little bit, and then it goes like that. In the upper part, notice that I'm actually going to shift the Q deviatoric is really being the additional one starting from this point, not from 0. We already had some amount of deviatoric stress because of the K0 condition. The points are going to end up here, and the contractive one will evolve in this direction. The dilative one may actually overshoot and come back, and it will look like that. So this is the contractive path, this is the dilative with overshoot, the contractive, the dilative, and here it is self-explanatory. This is the contractive and this is the dilative. This is the drain case. Now for the undrained case, we're going to have a similar situation, and please do them in detail. So this is Q P prime, void ratio and epsilon z. This is the critical state line. And we started with a deviatoric stress, but one was on the contractive side, the other one was on the dilative side. So notice that if it is undrained, we do not know what happens on the deviatoric stress because we have to measure the pore pressure. We have to measure it. But we do know what will happen in terms of void ratio, because if it is undrained and the system was initially saturated and there is no cavitation, this point has to find failure here, and the dilated one will find failure here. Therefore, we know where they will encounter failure, and now we go from the bottom up, and from this point, it tends to go, well, first of all, let's do this one. This will go like that, and this one tends to follow that, but eventually it goes in this direction. It tends to contract a little bit at the beginning. On this axis is boring because it's shear deformation without volumetric strain. So both the dilated one and the contracted one will follow horizontal lines. On this other plot now, one ends here, the other one ends here, reaches this maximum. This maximum is here, and this one is goes, and it goes like that. So folks, you will have to use a robust constitutive model to capture all these paths, to do it with the natural behavior of soils, which is not necessarily what you get with the simplest constitutive models, but you can grasp the trends by understanding the interplay between effective stress, volume change, and in the absence of volume change, effective stress and pore pressure generation. The last question is limiting equilibrium. Remember that there are two upper bounds and lower bounds, one being the upper bound being the kinematically admissible, and that one says that nature will always find a mechanism that is more effective than the one you will find. That means that we are going to start with a mechanism that is kinematically possible. For example, in this case, we are going to assume that the system could rotate. Sorry, this is not a circle, but I'm running out of space. And then it would just lift up this block. And so when we do moment equilibrium, we have to do moment equilibrium with respect to that point. We should actually do the whole energy computation, but it will give us the same result. The moment equilibrium with respect to that point, so is the addition of all the shear stress along the half a perimeter plus the weight exerted by this block versus the moment caused by the load, and that will give us an ultimate load. If the drawing is done right, this is B, and this should also be B. So this should be extended. Proper geometry is important. This is the kinematically admissible. The statically, it assumes a stress field that is compatible with the failure criterion and with the boundary conditions. So take a look at the element here and the element here from the outside and from the inside. And this is the load. So from the outside, if we start with this element, it already experiences vertical stress which is equal to gamma h, the unit weight of this block above. So you start with that one, and you're going to add 2SU, which is going to be the diameter of a circle, 2SU to get to the horizontal, and then you're going to add 2SU more to get to the Q ultimate. So you're going to get the Q ultimate is going to be 4SU plus gamma h. Verify that this is the case, and check whether one is an upper bound and the other one is the lower bound.